This video will be going over section 3.4, which is on the graphs of polynomial functions. The main topics in here, we'll talk about the factored form of a polynomial, how it relates to its zeros. Remember, that's the same thing as zeros, roots, x-intercepts, and then something that might be new called their multiplicity. Then we'll talk about the end behavior of a factored polynomial. This will pretty much be built on what we did last section. And the last, really one of the main topics of polynomials, dealing with them being functions and everything. We want to know how to graph them with some sort of precision. All right, so the first thing is the factored form of a polynomial. This is really kind of a fact here. I'm going to read as before. Whatever is highlighted is pretty much what I want you to write down. It says if f is a polynomial of degree n with a leading coefficient a, so that's the thing that's out front, and only real zeros, that means all the zeros are real numbers. We wouldn't have any eyes popping out anywhere if we tried to figure them out. Then it can be factored into the following form. So f of x equals a times x minus r1 times x minus r2, or however many we have, all the way down to x minus rn. Each of these r's are the zeros. And we'll see why that's the case when we work a problem below. And in case you have forgotten how to figure out zeros or what it means, we'll talk about that. One thing that's important, if some of the factors are repeated, we will express these with an exponent. So if we have x minus 2 twice, we would write just x minus 2 squared. The exponent is called the multiplicity of the corresponding zero. All right, so this is a pretty important idea. We'll see how it relates to the graphs, but if the multiplicity of something is even or odd, it means a lot as to what the graph looks like at an x-intercept. So multiplicities are important. All right, we've got a couple problems here just to talk about these new things and some old topics that you would need to figure out if you wanted to graph it. It says for the following polynomials, factor them if necessary. This first one is factored for us. The second one down here is not. And state the zeros and their corresponding multiplicity. The x-intercepts or horizontal intercepts, you might see it written on the homework, and the y-intercepts or the vertical intercepts. All right, so this one is factored. We want to figure out the zeros first. I'm just going to go in order. All right, so in general, when you figure out zeros of a function, you set the function equal to 0, meaning we'll have 0 in place of f of r, and it equals this whole thing. All right, now this one's very messy, but because it's already factored, there's not much you really have to do here. When you have it factored and it's set equal to 0, we now set each factor to 0, just like when you solved equations before. In order to factor, you have it equal to 0 first, factor it, and then set each factor to 0. And so don't forget about the thing in front, the negative 12r. We'll have that equal 0. We have r minus 2 to the 7th power equals 0. We've got r plus 3 equals 0. And we got 6r minus 11 squared equals 0. And we want to solve each one of these. All right, now to solve each one of these, start over here on the left. We have 0 equals negative 12r. If we divide by the negative 12, 0 divided by anything that's not 0 is still 0. So we got r equals 0. Now this exponent here is not really going to affect much, but if you want to be proper and get rid of it, which you should, you can either get rid of the 7 by doing the 7th root or raising each side to the 1/7 power. Just the same thing. I like to do the 1/7 power. The reason I like doing that is it's more beneficial when we go forward in the class as well to get exponents to cancel out, because the exponent rule will tell you multiply 7 times 1/7, which gives you 1. All right, but we got r minus 2 equals 0 to any powers, still 0. R minus 2 equals 0, and then we add the 2 to each side and we get r equals 2. This third one here, r plus 3 equals 0, we just directly can subtract 3 from each side. And we get r equals negative 3. No exponent there. And the last one here, same deal as the second one. We have to get rid of this exponent. Ultimately, you can just kind of disregard it, but to properly get rid of it, we can raise each side to the 1/2 power. Get those to cancel out. And 6r minus 11 was 0 to the 1/2, 0 to any power is 0. Now finish solving this for r. Keep in mind this doesn't have just an r in here, it's a 6r. We add the 11 to each side. We got 6r equals 11. And we divide each side by 6 and we get r equals 11 over 6. All right, now what you just figured out are all the zeros. We have 0, we have 2, we have negative 3, and we have 11 over 6. And now one thing that's important, if you recall, I just scrolled up here from the factored form, you see this minus. What you'll see when a polynomial is factored is if you have minus something, like r minus 2, the 0 is positive 2. If you have r plus something, the 0 is negative. Here we have r equals negative 3. That's because when you set it equal to 0 and solve it, you get the opposite sign. Going forward, when we have something factored, I'll probably just, excuse me, I will probably just kind of omit this part and just talk about each one. All right, the other thing that goes along with this is the multiplicity of each. The multiplicity, the way you would write it is it depends on the 0. And it is simply the exponent from that 0. Right, so for r equals 0, that came from this first term here, and the exponent was 1. Because we don't really have it written. So the multiplicity for r equals 0 is 1. I'm going to draw an arrow because it goes along with this 0. For r equals 2, that came from this r minus 2 to the 7th power. Its exponent was 7. So this multiplicity is 7. Just the exponent. For r equals negative 3, that came from r plus 3, which is to the first power. Once again, that multiplicity is 1. And the last one, r equals 11 over 6, that came from 6r minus 11 squared. The exponent is 2. The multiplicity is 2. Now the way I'd like to see this written, just kind of set up the excuse me, the homework will have you set it up the same way. When you have a 0, for example, r equals 0, below it or attached to it, you'll have the multiplicity of 1. If you mix and match these and don't write them in the correct order, it's not right. So 1 has to go with 0, the multiplicity of 7 has to go with 2, the multiplicity of 1 has to go with negative 3, and the multiplicity of 2 has to go with 11 over 6. Right, but we got the zeros. We got the corresponding multiplicity. The x-intercepts are pretty much what we just found as far as the zeros go, because remember, they're pretty much the same thing. They are just a coordinate pair. The x-intercepts are the x value of the 0, and the y value is always 0. So here we have 0, then we have 2 for x. The y value is 0. We have -3 for x. The y value is 0. And we have 11/6 for x, and the y value is 0. All right, so once you find the zeros, you've already found the x-intercepts. Just make sure you make them a coordinate pair in the proper way. The last thing we're going to ask for is the y-intercept. For the y-intercept, we plug in 0 for x, or in this case, r. Since that is our input value into our function. We got f of 0 equals, plugging in 0. Some of you may already see what's going to happen. We got 12 times 0 times 0 minus 2 to the 7th times r plus 0 plus 3, 0 for r, times 6 times 0, which is going to be 0 minus 11 squared. But all of this is going to equal 0 because what we have here is 0 up front, and we're just multiplying it. 0 multiplied by a whole bunch of stuff is still 0. And that means the y-intercept is also 0, 0. But there's only ever one y-intercept. There can be many x-intercepts, there doesn't have to be any. But for a polynomial, there's always one y-intercept. Right, so realistically, you won't really see equations this messy, but I just wanted to talk about all the key points. You don't want to forget about the stuff up front here when you find the zeros. And another thing that will be common, you don't want to forget when finding the zeros, you don't just look at the back here. You have to make sure you look at the whole thing. Right, we wouldn't want to say the 0 here is 11 because of the 6. All right, number 2 is one that we have to factor because it's not factored for us. Now this is going to recall on old techniques. There's nothing new in this section about factoring. The first thing to realize is we have an n in common. I'm going to factor the n out. We got -15n squared plus 14n plus 8. And once again, these are set up to factor. You do have the quadratic formula at your disposal if you need to figure out how to factor this. But we'll go ahead and factor it because it is factorable. So just to refresh you very quickly, when the number on the squared part is not 0, we do the AC method as one of the ways. So we multiply the -15, the a, times the c, which is 8. And -15 times 8 is -20, -120 rather. And we want two numbers that multiply to -120 and add to 14. And the two numbers for that are 20 and -6 are our two numbers. Now it's really up to, at this point, how you learn this, how you're going to go about doing this. You may have done this a lot of ways. You might only really know the guess and check way, which is fine. But for these numbers, there's a lot of things to guess. But one of the things I would say is, well, 15 is either 1 times 15 or 3 times 5. And 3 and 5 will only work with these numbers, because 15 doesn't go into 20. we're going to have all of a 5 in and all of a 3 in. It doesn't matter which one you make negative because it'll affect how you make the other thing negative. In fact, you know, one thing that might be a good idea, especially if you don't like the negative on the squared part, is you can factor it out. So I'm actually going to just go ahead and do that. It won't change what we did here, but I'm going to go ahead and go back and do it that way. It makes it a little more clear, I think. All right, so if we take out negative n instead, I'm going to take out the negative sign. We got 15n squared minus 14n minus 8. You'll notice here that the 20 and the negative 6, that's still going to be the same thing. Our a times c is still the same number. It's just flipped the sign. A is 15 and c is negative 8, but multiply those, we still get negative 120. What will change is that we now have to add to negative 14, so it'd be negative 20 and 6. All right, so factoring out the negative is something I usually do. I'm not sure why I didn't do it the first time, but I think it's a lot easier to have your leading coefficient be positive. All right, so we got, like we discussed before, we got 5n and 3n. 1 and 15 aren't really going to work. If we're going to make 20 happen, we got to multiply the 5n by 4 and multiply the 3 by 2 to make the 6 happen. And then to get negative 20, we have 5 times negative 4, get positive 6, we have positive 2 times positive 3. If you didn't take the negative out, you'd probably end up missing the negative sign. That's one of the common things when you factor. So that's why I like to just take it out. It's totally up to you, but bare minimum, you got to factor the in out to be able to factor this part. All right, now we want to do what we did last time. I'll remind you of the directions. We want to get the zeros, their multiplicity, the x-intercepts, and the y-intercepts. So the zeros, we set each part equal to 0 again. I'm going to go ahead and do that. We have 3 parts we got to set equal to 0. Do not forget the thing in front. And now if you solve each one of these for 0, the one on the left, we get n equals 0. The one in the middle, we'll subtract the 2 to get negative 2, and then divide by 5 to get n. So you can take the 2 steps you need to do that. And then for this one, we would add the 4 to get a 4 over here, and then divide by 3. And these are the 3 zeros. We got 0, got negative 2/5, and we got 4/3. One thing that you can find maybe a little bit interesting based on last section is the degree of our polynomial here is 3. The most amount of zeros we can have is 3, and we actually have 3. Right now, multiplicities, I'll abbreviate it mult. For each one, the multiplicity is 1 because on the n, that came from the front term. It is 1, and the exponent on everything is 1. Right, so they all have multiplicity 1. Now the x-intercepts, like we talked about above. You just take your zeros, those are the x values, and the y value is always 0 for the x-intercept. At 0, 0, negative 2 over 5, 0, and 4 over 3, 0. And then the last thing, the y-intercept. If we plug in x equals 0, or in this case, n equals 0, we got g of n. Now you can plug this into either one. You can plug it into the original, you can plug it into one of the factor ones. It's totally up to you. If we plug in 0 for n, we'll get 0 in every spot. And that'll give you 0. And then the coordinates for that would be 0, 0. Now once again, you'll always have one y-intercept for a polynomial. You can have more than one, you can have 0. X-intercepts, it's totally up in the air. You can have none, you can have 10, you can have anywhere in between. You can even have more than 10, but we won't see anywhere near 10. Alright, so that is the factored form of a polynomial. And once again, it's very important to realize when a polynomial is factored, you can pretty easily see the zeros. All right, the next thing is the end behavior of a factored polynomial. Now, this is definitely something that it's a little bit more challenging than the previous section. I'll show you why with a computation. But it's also one where it's a lot easier for me to make problems where I can make the graph not give you the right picture right away. So you have to remember what we did with the end behavior of a polynomial before. We looked at the leading term, which was the term with the highest power of x or t or whatever it was, and we found the end behavior of that. So the idea with doing it with this with a polynomial would have to be multiplying all this out to see our polynomial, figure out what the leading term is, and go from there. That's not going to be a reasonable thing to do. So multiplying 5t plus 6 to the 8th out isn't something you want to do. I have up here how we go about doing it. All you do is remove everything except the largest power of the variable inside each factor. Multiply the result together. This will be pretty short. And then determine the end behavior of that result, because that will be your leading term. All right, so what we're saying here, let f of t equal negative 4t times t minus 1 times 5t plus 6 to the 8th power times t minus 4 squared. We want to just multiply and get the biggest, the leading term, the largest power of t. Well, the front term 4t, negative 4t, it's by itself. You can't cancel anything with that. You don't want to get rid of the negative. That might affect things. You might as well just keep the 4 along. On the inside of the first term, we have t minus 1, and we only keep the largest power of t. We get rid of everything else. We're going to not include that minus 1. 5t plus 6, same deal here. We keep the 5t. We get rid of the plus 6. And t minus 4, we get rid of the minus 4 part. We keep the term with the highest power of t in each one. And now I'm just going to go ahead and write out what we're left with. We got negative 4t in front. And the second term is just t. There's no power to it. The third term is 5t to the 8th power. And the fourth term is t to the 2nd power. now from here, you want to simplify using exponent rules. This thing right here, the 5t to the 8th power, you have to raise each part to the 8th power. You don't necessarily need to figure out 5 to the 8th power. It's going to be huge, but I'll go ahead and do that. We got 5 raised to the 8th power, 390,625. Don't need to try to figure that out by hand. So we got 4t times t. And we got that 390,625 t to the 8th times t squared. And we multiply all this together. So the numbers here you see are -4 and the 390,625. We'll multiply those two together. Multiply this by -4. -1,562,500. And then look at all the powers of t. If we want to multiply these together, t times t to the 8th times t squared, we add the exponents. Right? T is just 1. 1 plus 1 is 2, plus 8 is 10, plus 2 is 12. If we multiply variables to exponents with exponents, we add the exponents. And so we got this huge mess, -1,562,500 t to the 12th. Now remember what we talked about last section, what matters for end behavior. Is your coefficient positive or negative? We have a negative coefficient, and is the power even or odd? And this is even. So a negative with an even looks like -x squared. And as we go both ways, to the left and to the right, the y value is going down to -infinity. Right, now you can graph this in the calculator. This number is so big and negative that you might not even see the graph. It might just be stuck on the y-axis. So that is one thing that can be a little worrisome. And you don't have to use x, or sorry, t, you just use x. But if we graph it, let's just see what happens. Actually, so you can see it pretty well. It's super steep, but it's as we go to the left and to the right, it goes down both ways. So it matches what we were hoping for. Right, so one of the things I wanted to mention is why this works. If you tried to multiply out our entire polynomial at the beginning, you would see that this is the leading term. And I'll show you that in just a second. All right, so what I'm about to show you, I took the original polynomial and I typed it into Wolfram Alpha, but you can use a lot of algebra softwares that'll multiply it out for you. And when you multiply this thing out, if you go down here to the expanded form, you'll see that the leading term is what we have. But there's no reasonable way you could ever figure out the rest of this by hand. It would just take forever. So that's why if we need to figure out the end behavior, we do it like this. And another thing I'll mention about this graph here is if you graph this, look at the scale of here, 10 to the 17th, 10 to the 18th. It gets so big so fast that you might not even see the actual graph if you do this. And so if you wanted to figure out this question, you really have to do it the way I showed you. But we'll go ahead and work another one similar to this. P of r equals 2 times r squared plus r plus 11 to the 4th power times r plus 3 to the 7th. Now, same deal here. Inside each factor, don't forget about the things in front. That's considered a factor. You want to get rid of everything that's not the leading term, the biggest power of r in this case. So inside this first one here, first parentheses, we want to get rid of r and the 11. R squared is the biggest factor. That plus r is doing nothing. In the second one here, we get rid of the plus 3. And when we do that, we got 2. Then the next thing we have r squared, and that's raised to the 4th power, times r raised to the 7th power. And we're just going to simplify this. So this first thing here, r squared to the 4th power, this is something where we multiply the exponents. That's our rule. The exponents there. We got our 2 out front. 2 times 4 is 8. We got r to the 8th times r to the 7th. All right, we took care of the parentheses. We got rid of that exponent, extra exponent. And now we can multiply these. R to the 8th times r to the 7th is r to the 15th. We add them. All right. Once again, recommend you trying to remember how to do this by hand. Don't rely on your calculator too much. If we want to figure out the end behavior of this, we notice that the coefficient is positive and that the degree is odd. So if the degree is odd and the coefficient positive, it looks like y equals x. All right, that's our line with slope positive 1. As we go to the left, it's going down to negative infinity. As we go to the right, it's going up to positive infinity. All right, but as far as these go, it's really what you want to do. You're bypassing, essentially you're bypassing having to multiply all this out by just doing the leading term thing. All right, so the next thing is polynomials and their graphs. The first couple we have here, they give you a description of a graph and we're going to figure out an equation. And the last couple, they'll give you a picture and we'll figure out the equation. And on these problems, there is just one right answer. We'll graph the polynomial as well, our answer, just to see that it works. So this first one here, it says find the formula of a degree 8 polynomial. We'll talk about that after we write down the rest. With leading coefficient 1. It has roots of multiplicity 3 at x equals 0. Multiplicity 3 at x equals negative 5. And multiplicity 2 at x equals negative 8. Right. The degree thing is the very last thing you worry about because it really works itself out. So what you want to do is write down that factored form of a polynomial. And so remember that the factored form, f of x equals a x minus r1. Because we have multiplicities here, I'm just going to put the multiplicities as the exponents. X minus r2 to the m sub 2 power. These are just representing whatever 0 I put here or root I put here, the multiplicity I'm going to put up in the exponent. And this one we have 3 different zeros, 3 different roots, so I'm going to just stop at 3. Now, if we pretty much read all the information we have here, the leading coefficient is a, and we are told that is 1. We're just going to plug in 1 there and leave it alone. All right, we have a root of multiplicity 3 at x equals 0. right? So what this is telling us is R1, the 0, is 0, and the exponent M1 equals 3. Right. The second one, we have multiplicity 3 at x equals -5. We got M2 equals 3, the multiplicity, our second multiplicity is 3, and the second root is -5. So R2 equals -5. And the last one, we have multiplicity 3, M3, sorry, 2. We have multiplicity 2, M3 equals 2, and the root, the 0, R2 equals -8. Now go ahead and plug in this stuff. Once we plug it in, you'll kind of see how it works. And you might not have to go through all the little steps here. But we plug in 1 in front, our leading coefficient. We have x minus R1, which is 0, and we're being raised to the third power. The multiplicity of 0 is 3. We have x minus R2, which is -5. And the multiplicity of -5 is 3. And we have x minus R3. I realize I wrote R2 here. We have x minus R3. R3 is -8, our third 0, and its multiplicity is 2. And now what you want to do from here, we don't really need to write this 1 because 1 multiplying stuff doesn't change anything. You can get rid of that. But just kind of clean the rest of this up. X minus 0 is just x. We can write x cubed. And x minus -5 double negative gives us a plus. We got x plus 5 cubed. Same thing here. Double negative gives us a plus. But we have our formula here. The only thing that is left is x, our variable. So this means we are done. All right, and as far as the homework goes, you just need to be careful. If it asks for the equation, it'll tell you type like f of x equals this. If it asks for the formula, it'll tell you just this. Just be careful about that. If you leave the 1 in here, it won't mark it wrong. But the one thing I want to do is just graph this thing so you can kind of see what happens with the multiplicities. There is a difference between even and odd, like I mentioned. I'm going to go ahead and graph that. Go to our y equals. We got x raised to the third power times x plus 5 raised to the third power times x plus 8 raised to the second power. I'm just going to double check it. All right, typed it all in right. And I'm going to hit graph. And I feel like the graph is too steep. Zoom out. My window. Right, so the only reason I am confused is we have zeros at 0, x-intercept at x equals 0, x-intercept at x equals -5, and -8, which would be right here. But I'm not seeing it on the graph. And from what I can tell, I did not type in wrong. So I think that it might be too steep for the graph. Let me try it in Wolfram Alpha. It's a little more powerful. So y equals x raised to the third power times x plus 5 raised to the third power times x minus or plus 8 raised to the second power. see, that's zoomed way too far out. Let's see if I can enlarge it. Of course, not free. All right, well, I can kind of talk about the combination of what I want to do here. So the multiplicity at 0 and -5 are both odd. And what that means for the graph is it's going to pass through the x-axis. If you have an odd multiplicity, the graph will pass through the x-axis. So to go, if I go to my graph here, the one we made on the calculator at x equals 0 and x equals -5, odd multiplicity, the graph passes through. It doesn't stop and turn around, it just goes straight on through. If for any odd multiplicity, that's the case. Now the thing about even multiplicity is it just stops and turns around. The reason for this is it's a lot like y equals x squared. That vertex just stops and then shoots back the way it came from. So it passes through x-axis. And if I go to the Wolfram Alpha, at least I could see 8 pretty well. I know it's very tiny on the screen. Let me see if I can zoom in. At -8, you can see that the graph is going down towards the x-axis and then turns back away. That's because the multiplicity is 2, which is even. Right, so we're going to do that when we figure out the equations of a graph with multiplicity, whether it's even or odd. So that's pretty useful and important. See, I'm not 100% sure why the TI-84 isn't showing that part of the graph. Like I said, my guess is that the numbers are too big and the graph gets too steep, so you can't see it, which is another one of those reasons why you can't rely on a graphing calculator too much. Right, but I have one more like this. It says find the formula of a degree 4 polynomial having a root. Oh, I guess the other thing I meant to talk about was the degree thing. If you add up the powers here, they add up to 8, which is the degree. So it works itself out. It's just sort of an added piece of information. Right, so the next one here we have find the formula of a degree 4 polynomial having a root of multiplicity 2 at x equals 2 and roots of multiplicity 1 at x equals 0 and x equals -2. And the other thing we are told is that it passes through the point 4, 480. So the thing that's very different from this problem from the last one is that this time we are told the graph passes through a point. Last time we're told the leading coefficient. Right, so what you're going to end up doing is you're going to make the equation and then plug in x equals 4 and y equals 480 to solve for the leading coefficient, which is represented by the letter A. Okay, we do not know what A is right away. We're going to have to solve for it. But we can set up our equation. We have f of x equals, or y, if you prefer y instead of fx, A. That's what we're going to solve for. It's unknown. Our first root, we are told, root of multiplicity 2 at x equals 2. That means x minus 2 is going to be a factor, and its power is 2. And then the other two things, sometimes the wording throws people off. It says roots of multiplicity 1 at x equals 0 and -2. It's saying they both have multiplicity 1. So x equals 0 as a root would give us x minus 0, and that's to the first power. And then x equals -2 to the root as a root would give us x plus 2, and that's to the first power. And I'll remind you the opposite sign is coming from the minus up here. All right, but go ahead and just simplify that up a little bit, and then we'll do this part. So f of x equals a. Now we're going to leave this alone, x minus 2 squared. X minus 0 is just x, and anything to the first power is just itself. So we can leave this as just x. And then x plus 2, can't really simplify that, but we don't need to write to the first power anymore, because we can get rid of the first power. It's understood. Right, but this is pretty much simplified. Now we plug in our 4 for x and our 480 for y. Just be careful that you don't accidentally plug in for a. That's the easy thing to do. We got 480 for y. A is our unknown. Plugging in 4 for x. And just simplify and solve. The right side, 4 minus 2 is 2. Do as much as you're comfortable with at a time, times 4, times 4 plus 2, which is 6. And then on the right side, 2 times 4 is 8, times 6 is 48. Yeah, 480 equals a times 48. And we'll finish up, divide by the 48. And 480 divided by 48 is 10. Right, so our leading coefficient is 10. Don't leave this as your answer. You need to make sure you plug it in. And our final answer, f of x or y, whichever one you need to use. It'll tell you in the directions. A is 10. We got x minus 2. I just realized I forgot to square this thing. Ugh. And my apologies, I forgot to square it, so I erased everything, because that is definitely going to make a difference in our answer. And we had our squared here, and I forgot to include it. But when we plug in the 4 and 480, the procedure is the same. 4 minus 2 is 2. Squaring that gives us 4 times 4, and then 4 plus 2 is 6. And now if we multiply that out, 4 times 4 is 16, times 6 is 96. We got 480 equals 96a. If we divide each by 96, each side by 96, 480 over 96 equals a, and 480 over 96 is 5. Once again, once you figure out a, plug it in, and then what you get plugged in is your answer. So f of x equals 5 times x minus 2 squared times x plus 2. And you could definitely leave it like this. I know some people like to rearrange it. They like to put the thing that's just x in the front with the 5, and that's fine. But it's not going to be marked wrong. So anytime you need to figure out the formula for a polynomial, given some description, or even when we get to the graphs in the next part, you're pretty much looking at what are the zeros, what are their multiplicities, and figuring out the leading coefficient. Is there a point on the graph I can see? Am I told the point, or am I just told the leading coefficient? All right, so for the graphs, they're all pretty much the same idea built on what we just did. When you're given the graph, you look at what your zeros are, which are your x-intercepts. You look at their multiplicities, and then you use another point, which is pretty much always going to be the y-intercept, because it's the only one you can really see on the graphs, to find the leading coefficient a. We'll go ahead and start this one by writing down the formula again. F of x equals a times x minus r1 to the m1 power, x minus r2 to the m2 power, x minus r3 to the m3 power. Right. I stopped at 3 because a 0 is the same thing as an x-intercept, and we have 3 of them. All right, you'll notice the numbers here. Hopefully it's not too blurry, but the number is -3 for the one on the left. It is -1 for the 0 in the middle, and it is 1 for the 0 on the right. And their multiplicities, the only thing you can really tell is if it's even or odd. But I'll tell you right now, if it's even, use 2, and if it's odd, use 1. Right, it works for every single one of these. If you use your multiplicity when it's even as 2 and odd is 1. Right, so remember what we wrote up here. You have an odd multiplicity if the graph passes through the x-axis. You have even if it stops and turns around at the x-axis. So if we look at where our zeros or our x-intercepts are, this one at -3 passes through. So the multiplicity there is 1. The one in the middle also passes through, goes right on through the x-axis, even though it turns around, it's not till after. So it's 1. And then at this last 0, 1, it stops and turns around. The multiplicity is even, and we use 2. Right, so I'll just kind of line it up like that. All right, so we've got the zeros, -3, -1, and 1. We got their multiplicities, 1, 1, and 2. I'm going to go ahead and plug that in. We're still going to have to search for a, the leading coefficient. And you can plug this in any order. Just make sure the exponent goes along with the correct 0. So for -3, we got x plus 3. And that's to the first power. The multiplicity of -3 is 1. The second one, I'm just going to go in order. We got -1 for our 0. We got x plus 1 when we plug that in. And its multiplicity is 1. That's to the first power. And then the last 0 we have is 1. We get x minus 1. And the multiplicity of that is 2. The power there is 2. And I'll just clean this up a little bit by getting rid of those 1 powers, because they don't need to be there. But don't do anything else as far as multiplying it out. This is plenty far enough. Right, so the last thing is to get the leading coefficient. After you've figured out everything else, we get the leading coefficient, and the y-intercept will tell you how to do that. So the y-intercept here is -1. Right, in that coordinate pair, x is 0, y is -1. We want to plug this in for x and y to solve for a. Let's go ahead and do that. Plug it in. Y is -1. Plug in a. We want to plug in 0 for x. Don't do this too quickly. Just take your time with it. All right, plugged in 0 for x's. 0 times 3, or 0 plus 3, sorry, is 3. 0 plus 1 is 1. 0 minus 1 is negative 1, but if you square a negative number, it becomes positive. So we get positive 1. 3 times 1 is 3. And we divide each side by 3 to get a. Yeah, a equals negative 1/3. And just like last time, once you get that a, you plug it in and you're done. But you gotta plug it in. Got negative 1/3. We got x plus 3. We got x plus 1. And we got x minus 1 squared. I'm running out of room, so let me just actually write that somewhere else. I'll write it below. It makes more sense. Got f of x, our final answer, is negative 1/3 times x plus 3 times x plus 1 times x minus 1 squared. And as far as graphs of polynomials, that's the ultimate culmination. That's really the more important thing when it comes to graphing in this day and age with graphing calculators. You can graph things pretty easily, especially with a computer, but being able to figure out the equation from a graph is very important. So as far as polynomials go, this is all you can really do.